In order to introduce magnetic fields to you, I think we should first look back at the types of fields we've already talked about. So we've talked about gravitational fields and we've talked about electric fields. So on the left you can see the Earth, and I've drawn this representation of a field because if you remember, a field is the area around something where something else experiences a force. So a gravitational field is the area around a mass where another mass experiences a force. Because the gravitational force is the force, the attractive force between two masses. So if you look at the Earth over here, it is going to exert a force on other objects around it, and how much force it exerts on those objects depends on, first of all, how close they are to the Earth, and second, how massive the other objects are. Okay? And so this region around the Earth that I've drawn in here, which is a representation of a field, shows you that in this darker, denser area, things will experience a greater force over here. And then as you move farther away from the Earth, it kind of fades out until it's just negligible. Okay, so a field is not necessarily a perfectly defined area that has a boundary where it stops and a boundary where it starts. It just kind of fades out to nothing. Okay, and that's what's happening over here. You get this dense area where things experience a large gravitational force, and then as you move outward from the Earth, they're experiencing a smaller and smaller force until it's just really so small you can't feel it anymore. So we can draw the Earth's gravitational field using vectors as well. And so these gravitational field vectors would point inward toward the Earth. Okay, because gravity is always an attractive force. Other masses are going to always experience an attracting toward the Earth. Okay, now when we look at electric fields, they work similarly in that they're an area around a charge where another charge experiences a force. And so you have the same kind of density area going on. The area around the charge right next to it is kind of this denser red, darker red, showing that other charges experience a greater force there. And then as you move farther away from that charge, you experience less and less force. Okay? They can be drawn with force with field vectors as well. It's just that with charges, the direction of the field changes depending on what charge is creating the field. Okay, so we have this positive charge on top over here. Electric fields are drawn as though they are acting on a positive test charge in the area. Okay, so we've said this a whole bunch of times if you've been following along. Electric fields point in the direction of the force on a positive charge. So if we think about this positive charge, what effect is it going to have on other positive charges in the area? It's going to repel them, right? Because like charges repel each other. And so the field around this positive charge, if we're using field vectors, looks like this. Okay, and how many vectors you use is not really all that important. It's just a representation of what's happening in the field. Okay, and so that positive charge is going to repel other positive charges, and so the field that we draw is pointing outward. At the bottom you also see a negative charge. You see the same kind of dense force density thing going on with the red, but in this case, because positive charges would be attracted to that central negative charge, the field vectors don't point outward, they point inward. Let's try that one again. Okay, and so that's our field around a negative charge. Now, a magnetic field is the same idea. It's going to be this area around a magnet where another magnet experiences a force, but it's going to act a little bit differently because magnets are a little bit weird. They have a north pole and a south pole. and north poles repel each other, and north poles and south poles attract each other. Likes repel, opposites attract. So we're going to do a few demonstrations that show exactly what's going on with magnetic fields. So here we have a regular bar magnet, and we're going to look at the shape and direction of this magnetic field. So we know that fields have magnitude or strength and direction to them. So we're going to try to demonstrate what both of those look like in the case of a magnetic field. So here's our bar magnet. Now I'm going to use some iron filings to kind of demonstrate the shape of the magnetic field. So just because I don't want to get them all over my floor, because they are very difficult to get back in their container, we're going to put a piece of paper over it that kind of matches up with our magnet. So there it is. Now I'm going to shake a whole bunch of iron filings over top of this thing to hopefully give you a sense of what the shape of this thing looks like. Now you can see some very distinctive pattern is taking place here. You end up with a whole bunch of loops. So on the back side over here, it kind of seems like they are sticking outward, sticking upward, and then once you get to the middle, you kind of get these curves going on. It seems like you've got loops happening. So let's just follow one of these things over here. Here's a set of filings that kind of seem to be forming a loop, and then they lay down over here, and then they loop back inward this way. So it seems like magnetic field lines either start or end on the South Pole and curve over to the North Pole, maybe the other way around. I think that we're going to have to deal with the direction thing a little bit differently. Okay, so this is what a magnetic field looks like, what the shape looks like. Now we're going to grab a compass and show you what the shape looks like, or show you what the direction looks like, I should say. So a magnetic field is defined as the area around a magnet where another magnet experiences a force. So a compass is a magnet, right? It has a north pole and a south pole to it, and it points in the direction of whatever magnetic field it's in. So when we take this compass and put it in the magnetic field that's created by the bar magnet, it's going to point in the direction of the field. Okay, so we define the direction of the field as the direction a compass would point when inside that magnetic field. Okay, so the compass needle lines up with the magnetic field lines. So let's start at the North Pole over here, and we can see that it points away from the North Pole. Okay, so our North Pole of our compass needle is pointing away from the North Pole of the magnet. And then if we move it around like this, the direction is changing. Now over here it's perfectly sideways. And now it's pointing toward the South Pole. And it points toward the South Pole, points toward the South Pole. And then it lays perfectly flat over here. So if we would draw this out, you would get what seems to be a bunch of looping field lines that start at the North Pole and end at the South Pole, according to where our needle is pointing. So a little bit later we'll draw that out. Now let's try the shape and direction of a North Pole and a South Pole right next to each other. Okay, we're going to do the same thing. Overlay our paper. And then we're going to pour some filings on here and then use a compass on this right after that to check out the direction. So here's the shape part. Okay, notice those loops again. So this time, this is the North Pole, this is the South Pole. The loops are looping from north to south or from south to north, depending on what we find with the direction a little bit later on. But it's always these loops going on. Okay, even if you look up here where it's a little bit farther away, you still have looping from south to north or from north to south. And then back here, you start getting looping not this way, but the other way. If you remember when we did the single magnet, the loops went from south to north or north to south on a single magnet. Okay, so you've got this kind of combination of two things going on where the two magnetic fields are interacting with each other, and they are also interacting with themselves. Okay, now let's check out using the compass what's going on with direction. Starting right in the middle where it's confusing. Perfectly sideways. Okay, so our loops over here were horizontal. And then when we move the compass this way, our loops are pointing inward toward the South Pole. When we move it this way, they're pointing outward away from the North Pole. Okay, that's on the bottom side. On the top side, the loops are pointing inward. The field is pointing inward toward the South Pole and outward away from the North Pole, and perfectly sideways right in between. Now, if we move it backward over here, now it seems like the main field is no longer the interaction between the two. Now we're just talking about the field that's created by a single magnet. Okay, we saw this before where the field was pointing perfectly sideways, creating loops toward the South Pole. So if we just do this, we get the same thing that we were talking about when we saw a single bar magnet. It's just that when we move in the interaction zone over here, then it starts acting a little bit differently. Now I want to show you something a little bit crazier. This is a horseshoe magnet. Think of it as though you took a bar magnet and bent it. That's really all it is. It's got a North Pole and a South Pole. I think this is the North Pole and this is the South Pole, but I don't remember. I might have mixed it up. It has a North Pole and a South Pole, and they are just really close to each other. So with a bar magnet, the North Pole and the South Pole are pretty far apart, and so they create a certain shape of field. With a horseshoe magnet, the North and South Poles are actually really close together, and so they make a totally different looking field. So we're going to see what this looks like with the filings and with the compass again. Here we go. Okay. Okay, so this is a little bit harder to tell what's going on, so I'm going to try to point out some things. So let's first of all look down here. In between the North and South Poles, the filings just kind of connect to each other. Okay, so they're following field lines between the North and South Poles. So you've got just field lines back and forth like this, just like up here. Okay, so you've got a field that's in between the two poles, pointing back and forth between the North and South. You also have down here, you can kind of see some loops down here going between North and South. So just like we expected before, our field lines are looping between the North and South Poles. Now if you look up here, you're also going to find loops. But there's no North and South Pole up here. Not really. But the way that a magnet works is that you progressively move, when you move from north to south, you get less and less north and more south. That's a strange thing to think about a magnet. Often we kind of think that there's this magic split point between the North Pole and the South Pole. This whole piece is the North Pole and this whole piece is the South Pole, but that's just really not true. A magnet starts very much north over here. This is the northest you can get, and it gets less northish. These are real words, I assure you. It gets less northish as you move this way, and more southish until you get to the very most southern point. Okay? And so this spot over here is more northish than this spot over here. This spot is more southish. And so you get these loops connecting even those points that are relatively more north and relatively more south. So you're going to get, in a horseshoe magnet, these loops in relative north and south poles because they can't loop all the way from the north to the south. That's just way too far. And so those field lines find smaller connection points to make. So now let's put our compass on here and see what that looks like. So, direction. Now, we can figure out which one of these two poles is the North Pole and which one is the South Pole because of the way that the magnet works, or because of the way that the compass works. So let's just put it over here. So this is pointing away from the North Pole, and it points toward the South Pole, right? Because south and north, they attract one another. Now, when you move the compass around, this is pointing toward the South Pole and also lining up with the field lines, pointing to the South Pole, but also lining up with the field lines. So south is not over here, it's over here, but it's not pointing to the South Pole, it's lining up with the field lines. Okay, and then when we put it over here, we get perfectly sideways. And then as we move around, then it points more and more away from the North Pole. Now, if we could put it in between these two poles, like this, then you'll see what the filings were doing there. They were connecting the two poles. If we move it up a little bit, it kind of does the same thing. It connects the two poles. So the last thing we're going to do is take what we've learned about the shape and direction of magnetic fields and use it to draw some field diagrams using vectors. So we've seen the shape and direction of magnetic fields using the iron filings and the compass, and now we're just going to put those two things together in a field diagram. So here is our bar magnet, and we're going to just draw those loops that we had like this. There you go. That's the basic idea. We can also draw these loops that come out the back end here. They're going to complete their loops all the way around. It's just too big to draw. Okay, the second part that we need to draw is the direction. So this is the basic shape of a magnetic field around a bar magnet, and then we need to draw the direction. So we said that the direction of a magnetic field is the direction a compass would point in that magnetic field. Okay? We could think of that another way. The compass points in the direction of the force on a north pole. Okay, so we could think of the direction of the magnetic field as the direction of the force on a north pole as well. Okay, it's just often easier to visualize what direction a compass would point if you put it in the magnetic field. Okay, so our compass would point in this direction. There you go. And so it's coming out of the North Pole, or the relative North Pole, and going into the South Pole. There you go. That's the first one. Our second one is the North and South Pole that we put together. So we saw that the loops happen something like this. Okay, so we had the loops happening that we saw with the filings, and now let's put the directions on. We saw that the field points in the direction of a compass, or it points in the direction of the force on a north pole. So a north pole would be attracted to the south pole, and so all of our field lines should point inward toward that south pole. Even these ones over here.
And they point away from the North Pole, so something like this.
There. You get the idea. So there's our North and South Pole together. And in case you were wondering, this is what a North Pole and North Pole together would look like, where the North Pole and South Pole field lines connected to each other because they're attracted to one another. The North Pole and North Pole field lines do not. They repel each other. North and North repel each other. So let's look at the last one. And here's that strange horseshoe magnet one. So we're just going to draw the field lines as we saw them with the filings. So it's going from north to south, in between the two like this, and then outside, something like this, and then we talked about those relative north and south poles. So we'll get field lines kind of going like this, from a more northerly point to a more southerly point. And then it goes around like this. And then we get those kind of loops all over the place. So we get the same thing going on over here to the south. And then we even get them up here, from the more north points to the more south points. Now, there are more field lines than this, but this gives you the idea of the shape of it. Okay, so again, we've got the shape that we got from the iron filings, and we got the direction from the compass. So the direction of the compass is that way because that's the direction of the force on a north pole. So a magnetic field has these looping shapes, and its direction is the direction of the force on a north pole.